Okay. Recording is now in progress. You are in CSC 1351. If you're in the wrong place, you can leave now. Let's look at the schedule. Today is 21st. And so today we are talking about binary trees some more. Yay! And then I think we're on to a new topic Wednesday. Yes, generic classes. We'll see. I might actually let binary trees, I might talk about them a little longer. And then we're down to the wire. So we've got our last regular lab this week. And then the week after that, your final projects are due. Final due. Any questions about anything that's coming up? And then we have our final exam on the 8th. Okay. Let's take a look at the slides, and the slides are really just a guide to the code. So haven't talked to you since last week. So we remember what binary trees look like, right? They look like that, ideally, if they're balanced. The left child is always smaller, the right child is always bigger. Actually, I mean, you can control the sorting of the tree, right? So when you instantiate a tree map, you can hand it a comparator, right? And then it will compare based on that thing. And here's how a tree might look if you just let it do its thing randomly. If you just add stuff randomly, and the data does come in sort of a random fashion, you might get something like this, which really isn't too bad, right? And then we talked about base node, binary tree visitor, and the binary tree code. And so today I'm going to take a look at node2.java. So node2.java, it's a different take on the same thing. So we're going to put most of the recursive methods in the B tree class itself on this one, and not in the node itself. So the way this is going to look is I have a character C, I have node 2 left and right, just like before. So this part is all kind of the same. I have a constructor which instantiates the data part. And then I have a toString method. I have a draw method, and that's it, right? So that's a simpler node class. But then I'm going to go look at the binary tree code itself. And I'm going to put all the recursion here. So I'm going to have a height method that takes no arguments. And that's going to return a height method that takes the head of the tree. And then inside that method that takes the head of the tree, that takes a node rather, I'm going to say if the node is null, then I return 0. So if I have an empty tree, right, that means the head is null. And this is going to return a 0 right off. And if it's not null, then we're going to get the height of the left and the right node. And then we're going to compare them as before. This is actually slightly simpler, right? Because I don't have as many comparisons against null, if I write it this way. But it's equivalent, right? And the code should kind of look the same to you. If you're fully understanding everything that's going on, you should see that this is just another way of writing the same thing. And the node count works a similar way, right? So we're going to call a helper method, as we call it, with recursive methods. We're going to say the node count, we're going to give it the head. And then if the node is null, we're going to return a 0. Otherwise, we're going to return 1 plus the node count on the left plus the node count on the right. And again, the zeros are automatically handled because of this on the top. Any questions? Just a reminder that your life is better if you ask questions than if you allow yourself to get lost. Because allowing yourself to get lost means you get a low score on a quiz and possibly the final at this point, and you can't afford that. Okay, all right, we'll continue. So let's look at the add method. So with the add method, I'm going to say if the head is null, I still have to do some special logic for the head here. So if I say if the head is null, then I'm going to assign a new node. Otherwise, I'm going to say add, and then I'm going to say the head and C. And so then I'm going to have my add method, my helper add method, which is going to take a node and a character, and it's going to determine if I've got a left or a right and which thing to add. So if C is less than n dot C, then I'm going to add to the left, and that adding to the left will either check a null and then assign, or it will do an add, a recursive add. And on the right, we do the same thing. If n dot C is less than C, we do the other thing. And if n dot C is equal to C, what do? Nothing, right. So both of these ifs fail and nothing happens. Bless you. So then we have a toString method, and that's just going to call the heads toString method. I have a draw method, which, you know, is HTML. You don't need to see all that again. Contains method. So my contains method, I want to find out if character C is contained in my tree. I'm going to call contains head C. So if node is equal to null, I return false. If node is equal to C, I return true. If C is less than node.c and contains left and contains node.left, then I return C, right? And likewise, if node.c is less than C, then I'm going to call contains on the right and return true. Otherwise, I'm going to return false. So this will also do a contains check, and it will do it with fewer, you know, calls to if something equal null. And I think that makes it look a little easier to read, but, you know, it's up to you what you think is easier. Any questions? Yes. Michael? Brad, shoot.
Do you have a remove method for this one?
I don't remember. Let's see if I do. No, I don't. I didn't put a remove on this one. So yeah, the remove is a lot of work, and I didn't duplicate it. But we remember who remembers how removes work? You remember? How do you do it?
First, you have to, if you're doing it, the node is the top one.
Right.
And if you're left and right are null, then it's going to remove itself.
Right.
If left is null and right is the thing, you're going to just replace with the top and the right.
Right.
If you're replacing, if you have both sides, then you have to take the smallest on the right, remove it, make the right that thing it just was removed from, and then make the left what it was.
Yeah, very good. I hope you caught all that. Brad was paying attention, and he knows how to do a remove.
Would it be the same logic here?
Yeah, it would be the same logic. If Brad is dropped in the desert with just a computer, he can remove a node from a binary tree. And maybe that turns into a coconut. I don't know. All right, very good. Okay, so I told you that, so up until now, right, what we've been doing with the binary tree is we've been looking at trees that have a character as their data. Now, obviously, that isn't what we want, right, in general, right? What we want is something that's going to have, it's something going to have a more generic data type. And what's a more generic data type than character? What? Bits is not a character type. It's not a data type. What is a data type? What is a data type in Java? Yes. Oh. A primitive data type is so char is a primitive data type. I'm trying to remember your name. Drew. I was going to say Drew. I really was. Okay. I wasn't 100% sure though, but I was going to say that. All right. Okay, so a primitive data type is going to be a very specific type, right? Char is a specific type. Int is a specific type. Not many things can be converted to that. So what is a more generic data type? Right, object actually would be the most generic object you could have, because all objects are type object. And any of the primitive types can be converted to wrapper types, which are also a type object, right? So the most generic type that you can have in a Java program is an object. But can I compare objects to one another and sort them? Can I? How can I do it? Well, not iterable. So if I want to compare two objects, if I want to know which one is less, how do I do that? Okay, so the objects need to be comparable. That's what I'm getting at. So you either need a comparator to compare the two objects, as you said, or the objects need to be comparable themselves. So for the purpose of making a binary tree, the most generic type we can have is a comparable, right? And so that's what we're going to do with node 3. With node 3, we're going to have, instead of char C, we're going to have comparable C, right? And what's going to change, what's going to be different about this code than the code with the character? Who can tell me? What's going to be different? Bless you. Oh. Okay, you're going to have to write your own compare to method for your type of object. That's true, but what I'm getting at is what's going to be different about the binary tree class and its node. What's going to be different there? Instead of doing something I used to do, I'm going to have to do something different. So when we made our generic sorter class, what did we change? We went from sorting ints to sorting a comparable. What did we change? Nobody remembers? Somebody must remember. I know that there are people who remember that just need to speak up. What did I change when I wanted to go from doing a comparable to, from comparing integers, right? How do I compare integers? Who can tell me that? Presumably no one's afraid to tell me that. How do I compare integers? And how do you do that in code? How do you know which one is larger or smaller in code? Greater than or less than. Okay, so I use greater than or less than to compare ints. What do I change if I switch out my ints for comparables? Yes, true. You have to use compare to. So I switch my less thans and greater thans for compare to. You all knew that, right? Right, okay. Don't have to start calling on people, do I? All right. Okay, so we're going to instantiate this with a comparable instead of a char, right? That makes sense. We're going to have a toString, and that's going to look the same. Nothing is going to change about this, as nothing is going to change about that print writer class. So let's go and look at the binary tree itself. Okay, so here I'm going to compute the height, and the height method doesn't change either, right? This is the same height method we just saw. We have the helper method for the recursion, which takes a node. We go into the node, we get the left and right, and it's done. Same thing with this, but now we're going to add. And so add is going to, this first method is going to be the same, but this helper method is going to be different. So the helper method, instead of having if C is less than n dot C, it's going to have C dot compare to n dot C less than 0. Right? This used to be C less than n dot C. And then this one used to be n dot C less than C, but now it's n dot C compare to C less than 0. And these are the only two things that I had to change, really, to make the code behave differently. Right? I swapped out the less thans for compare tos. That's all it took. Are we cool? All right. And maybe we should run some of these just because we like code and we like running code. So oh. Okay, so this is what the code did, is it produced this output. Let's take a look at the code itself. All right, so we instantiate the binary tree. And now what we're going to do is we're going to say we're going to take the character array named bigger. So we're going to take all these characters BIGGER, and we're going to do an add for each of them. Now the reason this works is why? Because I have the type is char, and what does add take? What type does add take? Yes, it takes a comparable. And is C a comparable? Is char C a comparable? No, it is not. So what does Java do? What is the term? Who knows the term for what it does? It's called autoboxing. Okay. So when Java converts, a cast is something that we do explicitly. When Java does it implicitly for you, when it converts a char or an int to an object, or vice versa, that's called autoboxing. So it's sort of boxing up the char value into an object and passing it along, if you want to think about the term that way. Okay, so that's why it works for this primitive type, is because of autoboxing. So now I'm going to ask for the tree's height and the tree's node count. Now the height turned out to be 4, and the node count turned out to be 5. So there are 1, 2, 3, 4, 5, 6 letters. How come I have a node count of 5? How come I don't have a 6? True. Because there's 2 G's. And a binary tree is what kind of object? It's a set. And a set must have unique items, right? Okay. So I print out the height and the node count. The height you can't really guess. And then I have a thing that draws the tree. And then I do a contains check for B, U, G, and S, right? And tree contains B, does not contain U, contains G, does not contain S. So that's all as we expect, right? And then if I look to see the HTML it generated, I get this. So I've got a B at the top. On the left, I have a null. On the right, I have an I. And inside the I, on the left, I have a G. On the right, I have an R. And inside the G, on the left, I have an E. So that's how the tree wound up looking. It's not particularly balanced, is it? Yes, Drew. Contains has complexity log n for a balanced tree. If the tree is not balanced, it can be n. It's somewhere between n and log n. Any other questions? You understand why a balanced binary tree gets log n, right? Because each time I step down the tree, I cut away half the possibilities that remain. Okay. All right, let's go back to my slide deck. So another way that you can handle compare objects is to use a comparator, right? So we can use a comparator instead of a comparable. And a comparator is going to be an external entity that compares the two things. Okay, so here's my my class, my node 4 class, and this looks just like my node 3 class, except instead of comparable, I just have object, right? So something even more generic than comparable is object, because anything can be an object. And then what I'm going to do is I'm going to take a look at okay, so now when I instantiate this class, I'm going to instantiate it with a comparator, right? And that's going to have to get stored along with the head. So now I have an additional field that I have to keep track of in my binary tree class in order to know how to sort my objects. And what am I going to change from comparable to comparator? Somebody else. Somebody else gets the glory of answering. What do I have to change if I'm going from comparable to using a comparable to using a comparator? Somebody else besides you. You answered a bunch of things today. Somebody else, somebody new. Yes, Bennett. Yeah, you're going to have to make your own compare. Well, you're going to have to make your own you're going to have to make your own subclass of comparator. And what method does comparator have in it? It has compare. So if you want to think about it, if I have a comparable object, I want to know what I compare to. But if I'm a comparator, I want to know which two things I compare. So it kind of makes sense from an English standpoint, if you want to think about it that way. But what do I have to change about my binary tree code itself? So when I went from using a character to a comparable, I changed the less than to an A dot compare to B less than 0. What do I change when I go from a comparable to a comparator? This shouldn't be a hard question. Maybe the hardest part is opening your mouth or raising your hand. I don't know. Somebody else, yeah, Bennett can do it again. Yeah, right. So I want to say C dot compare AB instead of A dot compare to B, right? That's going to be the basic change that I'm going to make. And you can see that down here. So it's called comp, right? So comp dot compare C comma N dot C. That's going to be the same as C less than N dot C. Okay, make sense? You're following me? Anybody have any questions? People with puzzled frowns, do you have questions? It's always a favorite of mine when I ask a student, do you have a question? And they say, no. Yes, Drew?
For the second if statement, is it possible to keep it as compare and keep the C and not C and make it?
Yes, if I could reverse the two orders and make it greater than 0, I could say and C comma N dot C greater than 0. That would be fine. It would do the same thing. Any other questions? All right. And then we have our draw method, and then everything else is the same. And this main method is actually the same. It's going to do the same thing and give us the same answer. Okay. Make sense? Now, the binary tree class in Java, the B tree class in Java is going to have, it's going to have the option to be instantiated with a comparator. And if you don't, you better give it a comparable, right? So you have that option there. So it can be sorted however you want it sorted. All right, let's go back to the slides. So now that we've got all of that wonderful stuff, oh, and here's the comparator that I used. So there's the comparator that I used for this thing. So it was comparing two characters. So I just had an object A and an object B, I cast them and I returned the difference, right? Because character is a numeric type, and so I can subtract it. Make sense? Okay. All right. Min map. So now that I've got a working set implementation with a binary tree, I want to remind you of the min map class. Remember, we had this class before, and we implemented the hash map with it, right? And so we're going to implement that again. And we're going to have my tree map. And so what's going to look, so the difference between my tree map and the binary tree that we've been looking at before, is that it has a key and a value. Now, I probably should have made this key final because we all know that we can't afford to change the keys. But I just didn't happen to do that. Okay, so I'm going to instantiate this. I'm going to have a constructor that takes a key and a value, and it's going to update the two fields. And then my add method is going to use a comparator, is going to use a compare method. So it's going to look at key and this dot key. And if they're equal, then it's going to update the value. So before, what happened when we had the set and we got something that was equal to the key, what did we do? Nothing, we ignored it. In this case, of course, what we're going to do is we're going to update the value. Otherwise, if this is less than 0, we're going to add to the left. And if it's greater, we're going to add to the right. And then I have an add left and an add right method. And the add left method is going to say if the left is null, then left is equal to the new node with a key and a value. Otherwise, it recursively calls the left add. And same thing with the right. I just swapped the words left and right, and it's all the same. Any questions? Yes, Drew. No, if it's equal in the regular hash map, it also updates the value on the node. Does the same thing, right? The difference between the binary tree and the hash map is just the data structure, the way we're keeping track of when something is equal. Okay, and then we're going to have a get method. Okay, so I have a get method on this class. So I'm going to find, it's kind of like a contains, except the difference between contains and get, right, is I have a value now on my tree. So I'm not just going to ask if the key exists. I'm going to ask what value is associated with that key. And so I'm going to do the same thing as I did before. I'm going to do this comparison. I'm going to find out, and that's going to give me an integer back. And if that integer is equal to 0, then I'm going to return the value. If it's less than 0, I'm going to go down the left side. If it's on the right side, I'm going to go down the right side. And then I have a get left and a get right, which just say if the left is null, return null. That means I didn't find anything. And if it's an otherwise, I'm going to recursively call the method. Now, my comp method is going to just cast the key to a comparable and call the compare to method. So even though I didn't put comparable as my data type on the class, if I give it something other than a comparable, it's going to fail, right? Any questions about that? Yeah, Drew.
You go back to the
So the get and the put kind of look the same, right? It's just that what do you do when you find the key? Do you update the value or do you return the value? That's the difference between the get and the put. Yes.
When later down the tree splits again, how do you get to that split? If the tree splits left and right, it's an error.
So when I call a get method, right, it's gonna check for left or right, right? And if I call a get left method, then it's gonna recurse to the get method. I mean, it's just kind of a, looking at this, the way I wrote this code, I could easily have written it so that I didn't alternate between the left and the get, right? But I just happened to write it that way. And there's probably a dozen different ways to write the same thing. And here, if I wanted to, I could check for the existence of a comparator. And if I have a comparator, I could use that. And if otherwise, I could cast to comparable. That's a thing I could do. All right. And my size method looks very much like, what you've seen before. And then I have my tree map, which is the container. So it's going to have the root or the head of the tree. It's going to have the root of the tree here, and I'm going to have my put. And if the root is null, then I'm going to create a new node there. Otherwise, I'm going to call the add method on the root. And similar with the get. And if I want to clear my tree, I just set the root equal to null, and the garbage collector clears out the whole tree. If I want to call the size method, if the root is null, it's 0. Otherwise, I call the root size method. And then I have fill lists. So what I'm going to take is a list of objects and a node M. And then I'm going to, what am I doing here? Let me take a look at this. Let's not add. Must be another fill list method somewhere. I don't know what I was doing there. I don't know what I was doing there. Okay. Then I have my iterable keys. So, oh, I see what's going on. So I have my iterable keys, and I'm going to create an array list, and then I'm going to fill list from the root, and then I'm going to call that. So what this is going to do, the fill list is going to take whatever I have starting with node M, and it's going to fill in the list object with all the keys. So it's just kind of a cheating way to do an iterator. So if n is null, right? If the node I'm getting is null, then I'm just going to return and do nothing. If the node is not null, I'm going to add the key to the list, and then I'm going to call the left and the right methods, the left and the right nodes on the n, and I'm going to recursively add everything in those two subtrees. Now, this won't add things in sorted order, will it? If I wanted to add it in sorted order, what could I change? Anybody have an idea? Yes, Drew. It's simpler than that. I'll tell you this. It's a very simple change to the fill list method to make it fill everything in order. Yes.
Would you just add a fill list in between left and right that adds n? So it adds all the left then and then adds all
Yes. So Brad is right. So I would essentially, but he didn't quite say what I was thinking, right? So you switch these two lines. You switch these two lines, and then it will do it in order, because that way it'll go first down the left side, then do the middle, then do the right side. And if I just switch those two lines, then it adds everything to my iterator in order. And then when I go to get my iterator, I'm just returning the iterator of the list. Make sense? All right. Now that you've mastered all of that, I'm going to talk about some other things. So there's a red black tree.java. Before I go into that, let's talk about this. So there's a thing called a red black tree, and it's a form of balanced tree. It's a mostly balanced tree. It tries to keep everything with, the difference is never more than 2. And let's take a look at. So I don't expect you to fully understand the red black tree algorithm. It's a bit detailed. And at some point in your computer science careers, you will have to, really dig in and fully understand it. But for now, we're just going to go over it lightly. But here are the basic rules for the red black tree. So every node on the tree has got a color. It's either red or black. And the root is always black. And a red parent cannot have a red child. So we don't have 2 reds in a row. And then all descendants of a node have the same number of black nodes. And then all leaf nodes are black nodes, right? So that is giving a heuristic so that it goes like checkerboard fashion, ideally, where you have red, black, red, black. And by keeping track of these rules, we're able to approximately balance the tree. And so what's going to happen is when you add things, sometimes you're going to have to call methods like fix double red. And that can be complicated. But what I want to do is I want to look at the fix double red method. So what we want to do is we want to balance an unbalanced binary tree. And this part is something I want you to understand. Okay, it's actually what I'm asking you to understand. The subset that I'm asking you to understand, I think, is quite simple. So what I've done is I've drawn a tree in ASCII art, right? And I've got 3 nodes, N1, N2, and N3. And I put them in the sorted order so that N1 is to the left of N2 and N2 is to the left of N3. And likewise with the T's, they're all going in numerical order. Now, what I want to do is I want to balance this tree. And before I balance this tree, what I'm going to do is I'm going to say N1, I'm going to fill in, I'm going to give these things all names that sort of match things. All right. So what I'm saying is the top of the tree, starting from the current node, is N3. So I'm going to assign N3 with this, right? And then N2 is N3 dot left, right? So the current node with the left. And N1 is the left of N2 or the left of N3, right? So hopefully what you will be able to do is take a picture like this and assign these 3 ends. And likewise, you should be able to take that same picture and assign the T's. So that the left T, the T1 is the N1 dot left, T2 is N1 dot right, T3 is what? N2 dot right, and T4 is what? And 3 dot right. Yes. So that's pretty simple, right? You can do that. And then another possibility is you have, you can have a tree like this, right? So you have N1, N2, N3 with the T's arranged this way. And another possibility is you can have a tree like this where everything goes to the right, or like this with everything going that way. And in any case, any of these cases, what I want to do, the thing I want to have is a tree that looks like that. Okay, I want to have a tree that looks nice and balanced with the T's all leveled out. And the way I'm going to do that, okay, is I'm going to, I'm just going to fill this in. So the left of N3 is going to be T3, right? So N3 dot left is equal to T3. N3 dot right is equal to T4. Likewise, N1 dot left is going to be T1, and N1 dot right is going to be T2. Again, I'm just directly matching things to the picture that I drew with ASCII art. And then I'm going to say that N2 is going to be my new top of my tree, and N2 dot left is going to be N1, and N2 dot right is going to be N3. And this tree also keeps track of parents. So I'm going to set N1 dot parent to N2, N3 dot parent is N2, and N2 dot parent is GP. And GP is, where did I set that? I must have done that at the top. And GP is the parent of the current node. So it's the grandparent. That's why it's called GP. Excuse me. All right. And then after I've assigned the parent with the grandparent, then I have some other logic. I'm going to make sure, for instance, that the parents of the T's are set correctly. And then I have some assert statements to check that I've sorted everything correctly. Now, as I say, the part of it that I want you to understand and I want you to be able to do is I want you to be able to take these ASCII art pictures and first, like, be able to fill in the nodes from the names I've given you in the picture, and then to rewrite the tree with the nodes that I've given you in the picture. So what this is going to do, this process of going, to ASCII art and from ASCII art, is going to rebalance a subsection of the tree, right? And if you call this method recursively on the right parts of the tree, you can get the tree balanced or approximately balanced.
Question.
Yes.
So we would be given basically like a fill in the blank.
Yes, you'll be given like a fill in the blank and some ASCII art.
Yes. And we got given code.
And then you've got to fill in, you've got to pick the right options to fill everything in. Hopefully it will be easy. Yes.
Is it going to be like that, like N3?
It's going to be similar to that, right? I'm going to try to make it similar, but not exactly the same. That's what I usually strive for. So, so that's a thing that you can expect to see. So now you have if you've understood everything I've said, you have completely mastered binary trees. How many people feel they have completely mastered binary trees? Well, two sort of. So that's like one person if you add them up. If you don't feel you've mastered binary trees, you really should ask me a question. You should say, here's the thing I don't understand about binary trees. It's X. Explain X to me again. I mean, part of this isn't going to make sense until you try to code one yourself. Nothing can substitute for that. But all you people who claim not to have perfectly understood binary trees, you should have a question, at least one. Dig into your souls and search for that question. Yes, Logan. Yeah, okay, so what's going to happen with this tree is, in addition to keeping track of a left and right, we're keeping track of a parent node, right? So we're going to know which way to go up. So N1 knows its parent is N2, and N3 needs to know that its parent is N2 also, right? And what I want to do is I want to reshuffle this thing in place. So you see that N1 used to be on the top here and here, and N3 used to be on the top here and here. And when we reshuffle the tree, we want N2 to be on the top. So what we have to do is we have to go tell the grandparent, hey, us kids down here are shuffling ourselves around. N2 is our new leader. Okay, that's the reason. Now, I kind of did something similar when I wrote the remove method on the first binary tree class, because that returned the node that the new node. And that's kind of a similar thing, right? Instead of having a parent node, I just had the method return a node that's the new leader. Yes, Drew.
Explain how to how it goes to finding specific element.
Yeah, so all it does, right, is so here's the map version, right? So if I want to add something to the map, I have a key and a value, and I'm going to do a comparison, and that comparison is just going to call the compare to method and give me the integer back. If that integer is equal, then I'm done. I found what I was looking for, and I can update the value. If it's less than, then I need to recurse down the left side of the tree. If it's greater than, I want to recurse down the right side of the tree. And that recursion is what makes the tree work. Right. So every time I look at the tree, I look at it one node at a time, and I say, is this the node I want? If not, do I want the less than or the greater than? And then when I get to that node, I make the same choice. I say, is this the node I want? If not, I take the less than or the greater than. And in that way, I walk down the tree until I either find what I'm looking for or I fail to find it.
That's what makes it.
Yeah, that's what makes it work.
Exactly.
So the place where you normally have the choice in Java is when you're using a map or a set, and you can use a tree set or a hash set. And the general trade-off is you expect the hash stuff to be faster for most things, but you want to use the tree stuff if you care about the sorting, right? So hash will not sort it for you, but tree will. So that's the basic difference. Yeah, if you want to get everything out of the tree in order later on, you would definitely use a tree. And if you don't care about the order, you would probably use a hash. But the nice thing about Java is it's got these interfaces, right? So you can say set and map, and you can switch the implementation depending on what you want to do. Yes.
You go back to the red flag tree.
Yes.
Java.
Yes.
So I'm just curious, like, if you look at, like, if I can you scroll up.
Yes.
Yes, that one. So, for example, N1 equals this, that would be no. That is the root of the node.
Yep. Yep. Depending on the way the picture is drawn, the thing on the top is always going to be well, N1 is at the top, so this goes to N1.
Technically, we can look at something that if it's assigned as this, then we can assume that's the root of the node. And do right, left, right, and just.
Yep. Yep. Correct.
So some frizzy thing. If you do like root nodes, right dot, right dot, right dot, right, just go straight down to the right.
Yeah, you can encounter nulls. It's possible, right? But what I'm saying is, with this tree, I've already checked that I can go from N1 to N3 and N2. The ends, I'm saying that the ends are not null, but the T's might be. All right. That was a lecture. I hope you enjoyed it.